Okay, so let's give you a quick introduction on what happens in a circuit when. This is kind of a sneak preview of what we're going to do next week. And I want you guys to get thinking about it and looking at it. When I have a circuit, and let's go ahead and do it as a parallel circuit first. And that's what we worked on last week. This week we're working on series circuits in capacitors. So let's go ahead and look at this as a parallel circuit. If I have a source of power, 100 volts, AC, so it's alternating current at 60 hertz. Every cycle happens, a cycle happens every 16.66 milliseconds, so 60 times a second I have a cycle happening on this. It goes high, crosses zero, low, crosses zero, back again. And on this circuit, I'm going to put in a resistor, a capacitor, and an inductor. So I have two reactive elements and one resistive element. So this is a parallel circuit, so the same thing is true in this parallel circuit as every parallel circuit. And that is that the current is divided. A parallel circuit is a current divider. The voltage is the same across everything in parallel with each other. So right now I've got a resistor in parallel with the source. I've got a capacitor in parallel with a resistor in the source, and I've got an inductor also in parallel. It doesn't even matter what position I put those in, right? You as electricians, it's the same as where I put the breaker in the panel. You know, for almost every operation, it doesn't matter. It's still going to get me my source voltage because every one of those breaker spaces hooks into a parallel spot on that panel. Let's go ahead and give these some values. Real easy values that I like. 50 ohms. Let's go ahead and give this guy, well, let's solve our X sub C's and all. So let's go ahead and call this 75 microfarads. And then the unit for inductance is henries, right? So let's call this guy 200 millihenries. And off the top of my head, I don't even know what those are going to come out to, but I know how to solve them, though. So let's go ahead and solve first X sub L. So that'll solve my ohms value, my reactance at the inductor, if I go X sub L equals 2 pi Y. And we've done this 100 times. So I'm going to multiply 2 times pi times 60 hertz, times 0.0202, essentially, 0.0200. Because 200 millihenries is 200 thousandths of a henry, and 200 thousandths is 200 out of 1,000, which is the same as 2 out of 10, right? Which is the same as 0.2 or 0.200. I'll make sure everybody's clear on that one. We're in millis and micros. If we had another 6 weeks, we could do scientific notation and talk about all that, and it would make things a little bit easier. But let's go ahead and make that math clear on clear. Sorry about this, but I'm going to set my timer so this one doesn't go off either. I'm going to set this for like 23 minutes. Hopefully we don't go any further than that. So 2 pi FL, 2 times pi times 60 times 0.2 equals 75.4. I actually got 75.398, but I'm going to round that 9 up to 0, which makes it 75.4. So 75.4 ohms is my inductive reactance. And then at my capacitor, now that was without invert, right? Because 2 pi fly is the thing for that. X sub C equals 1 over. So it's the same formula inverted. 2 pi F, and obviously without the L, I need the C because we're now in capacitance. And 75 micro is going to be 0.00075, right? 75 millionths of a farad. So I'm going to go 2 times pi times 60 times 0.00075, 0.00075. Count them out, say it out loud, do it, enter. And that gives me a big ugly number, which I know can't be right. Oh, that's right, I got to invert it, because it's 1 over. It's that number inverted. So I'm going to go x to the negative 1, and it gives me answer inverted, enter. Boom, and I get 35.367. I think that's the same number we had last time, which I rounded to 35.37 ohms. Don't have to do anything at resistance, I've got 50 ohms. Now, here's the thing that's different about this circuit than the last circuit. What we've been doing up till now is drawing a triangle. Well, I should draw just the triangle part. We've been drawing a triangle. I'm getting ahead of myself. And I've been putting in my X here, my R here, and over here I would get my, no, I'm getting ahead of myself, aren't I? We are going to get there, but what kind of circuit is this? I just started solving it like it was a series circuit. I was going to take my X's and my R's and come up with Z. But I can't do that, right? What's the Pythagorean relationship in this circuit? Those of you who caught me and are yelling at the camera, thank you. My Pythagorean relationship is in the currents. So I need to solve each one of these currents. I've got 100 volts across this, I've got 100 volts across this, I've got 100 volts across this. So I'm going to solve I at the R equals E over R equals 100 divided by 50 equals 2 amps. I'm going to say I at the C, at the capacitor, equals E over X sub C, and that equals 100 divided by 35.37. And I need my calculator for that. 100 divided by 35.37, and that equals 2.83. A little bit of rounding there because it was actually 2.827, so I rounded 27 up to 3 because that's 7. 7 bumps me up. 2.83 amps. And then I at the L equals E over X sub L. And that's 100 divided by 75.4 ohms. That's going to be my smallest one yet, right? 100 divided by 75.4 equals 1.326 amps, which I'm going to round to 1.33 amps. 1.33 amps. So I've done a little rounding there. I've done it in the right direction, but there is some rounding, so I will have some rounding error. So now I've got this current, and this current. Now, this is where I would normally draw my triangle. It's like deja vu, right? And on my triangle, I would be solving for I total. And on that triangle, I would have my I at the R, and I would have my I at either the L or the C, right? And I would take the Pythagorean relationship. Well, here's the thing. The Pythagorean relationship works because there is a 90-degree relationship between the current in this case through the resistor and the current in the capacitor. They're 90 degrees from each other. There's also a 90-degree relationship between the current in the inductor and the current in the resistor. They're 90 degrees from each other, but here's the crazy thing. They're 90 degrees from that resistor in two opposite directions. So I've got current 90 degrees from the resistor here, but I've got current 90 degrees in the other direction from the resistor here. And in fact, if I were to draw the vectors, it would look like this. I'm going to have current at the inductor that's 180, because remember, 90 and 90 is 180, 180 degrees different than the current in the capacitor. But my resistor, my current at the resistor, is still 90 degrees to either one. So when I teach this and I have a live class, we usually do a demonstration about, well, who's got what pickup truck with what horsepower. And we have somebody with the big stump-pulling Dodge or Ford, and then we got somebody with their medium-sized Toyota pulling this way, and then usually we draw this one as a little weenie one. This is like somebody's Datsun or some moped or something. We say, what's actually going on here? Well, it turns out that moped just takes away a little bit of this. It actually reduces the size of that vector. And I still have a 90-degree pull from my Toyota or whatever. So when I pull my stump is still going to pop out that way, right? That stump pops out of the ground if these are chains and trucks pulling on this thing. It's kind of how vector math works. Well, we don't have that luxury of a live class right now, and so I can't pull the class to find out who's got the biggest monster truck to pull a stump. So what I'll tell you is this. Draw your triangle like this. It now looks more like a flag than a triangle. And I'm going to have I at the L and I at the C. Now, Which one has more? Do I have more current at the, here they are. Do I have more current at the inductor? I have 1.33, or more at the capacitor. I have more at the capacitor. So my capacitor is actually going to be bigger. What I do is I take the difference between these two things. So in this case, I've got 2.83 and I've got 1.33, and I'm going to subtract, and I did that backward, didn't I? 2.83 amps at the inductor. I just did it backward again. I don't know why I can't do that right. 1.33. Lucky for you guys, I'm lazy and don't fix these things, so you can laugh at me. 1.33 amps and 2.83 amps. So already I know that this is probably a capacitive circuit. When I go to do Eli ice, I'm probably going to get capacitive because I've got more current at the capacitor and I've got the same voltage everywhere. So my power, which is the thing that decides whether it's capacitor or inductive, it's going to be bigger at the capacitor than it is at the inductor. But in the meantime, solving for this, I simply take the difference between those two. And in this case, it's going to be C. So my resultant triangle is going to look like this. And it's just going to be I at the C and I at the R up here. And this is going to be my I total. So what I do is I subtract. I go 2.83 minus 1.33. Luckily, this math is easy. 8 minus 3 is 5. So that is 1.5 amps. So I should have 1.5 amps here on this. Now, I've drawn this in such a way as I think I'm going to confuse some people. Let's try and do this again. Here's my triangle. My R is 2 amps. I had, let's go ahead and put the X sub C up here just to make it easier. 2.83, and X sub L is 1.53, 1.33. When I subtract one from the other, I get rid of the X sub L, and all I've got is X sub C. But I no longer have 2.83, I have the resultant 1.50 amps there. Because this 1.33 amps that the inductor was pushing the other direction, they cancel out 1.33 of the 2.83, leaving 1.5 amps. So my resultant triangle is just the capacitor and just 1.5 amps. So when I do my Pythagorean relationship to solve I total, I'm going to only use these two values. And this no longer is X sub C, it's just X. Because this 1.5 amps takes both into consideration both the current at the inductor and the current at the capacitor. And I said that backward. The current at the capacitor and inductor. Both of those two things are this result. They're pulling in opposite directions, so one cancels the other. In this case, the capacitor had more current, so it wins, and I have leftover capacitive current. But at this point, it's just X. So I'm going to say I total equals the square root of, let's see, I at the X squared plus I at the R squared. Because remember, we're in currents, which is the same as 1.5 squared plus 2 squared. Whatever that is, take its square root. I don't know, 1.5 times 1.5 is like, what, 2 1/4 or something? I don't even know. Clear. Come on. 1.5 squared, just for fun. Yeah, it is 2 1/4. Plus 4, 2 squared is 4, equals 6.25, second square root. Second answer is 2.5. 2.5 amps. Should be my I total. So if you wanted to solve Z now, instead of using that big, ugly formula in the book that puts Pythagorean and reciprocal together into one formula, which God knows how anybody can use that thing and hit all the numbers right in their calculator, I can just use Ohm's law. And I can say Z equals E over I, right? Because that comes right out of this. EI, in this case, Z. Usually it's R. Z equals E over I. And so that's 100 divided by 2.5, and that's going to be 4, right? 100 divided by 2.5 is 4? No, that's wrong. 100 divided by 2.5 is 40. That's not right. Sure it is, because I'm not solving for, wow, I'm showing you guys all my best tricks, huh? I'm solving for Z, which is in ohms. So total Z is going to be 40, which makes sense, because in parallel, I know that my total impedance is going to be less than any of the individual impedances that I have on here. And I've got 50, I've got 35.37. Well, these two cancel each other out, so it's still less than that, 40 ohms. Where do we go from here? So now that and I'm not asking you to solve Z. I'm not sure why I threw that in there just because I could. Total current is 2.5 amps. I've got all those. I want to solve my powers now. I've got my volts and I've got my currents. Let's draw my currents up there so don't forget. So at this, I've got 2 amps. At my capacitor, I've got 2.83 amps. And at my inductor, I've got 1.33 amps. Right? I'm going to erase this triangle, even though this triangle will be useful later, but I'm going to erase it anyways. And I'm going to solve now my powers. So, E at the R, E at the C, E at the L, right? And now, these aren't powers, Jack. I really should redo this video, but I'm not going to. Power true is the power at the resistor. Power reactive at the capacitor. Power reactive at the inductor. And then I could just say PC and PL there too, but I want to make sure. And then power apparent, right? That's going to be my powers total. So power true is going to be easy. Power true is I times E at the resistor. I've got 2 amps and 100 volts, so that's going to be 200 watts. 2 times 100 is 200. And then I've got power at the capacitor. Well, that's also I times E, but it's the I at the capacitor. So it's going to be 2.83 amps times 200 volts. So it's going to be 283 twice, because 2.83 would be 100. And since I'm in front of a classroom or a camera, I should actually just do it. 2.83 times 200, that equals 566 var, right? And then at the inductor, I've got 1.33. Now that one I might be able to handle times 200. So 133 and 133, right, is going to equal 266 vars. Now, same thing again. I got my triangle, but I'm going to have vectors going in 2 different directions, each 90 degrees to my power true. So I've got to take those two, and the first thing I do is solve the difference between those. So at my C, I've got 566 vars in this direction, and at my L, I've got 266 vars in this direction. They're pulling against each other, so the one cancels the other out. So 566 minus, that isn't right, is it? Yeah, it is. 266, that equals 300. So my resultant triangle is going to be 300 vars, and my true power is 200 watts. And my PA is going to be 300 squared plus 200 squared, square root of 200 squared, I did that wrong, 200 squared plus 300 squared equals 130,000 second square root, second answer, and that equals 360.55. Let's see if I rounded that correctly. Nope, should be 360.56 VA. So really, we're not doing anything different in this than we are in the individual inductive, resistive, or capacitive resistive circuits, except that once we've solved something that requires a triangle, we're taking the difference between whatever's happening at the resistor and whatever is happening at the inductor, because those two are opposites of each other and they pull in two separate directions from each other. So some funny things can result from that when we start thinking about harmonics, but that's another week in another chapter. So now to power apparent, I solve 360.36. And then I'm going to do power factor. Now power factor is the same as it's ever been. Power factor is going to be power true over power apparent, or watts over VA. And it's going to be my watts, which nothing changed, 200 divided by VA. My VA has already taken this into consideration, the fact that I got two different things, and I've solved that. 360.56, I didn't have a decimal there. 360.56, 200 divided by 360.56. 360.56 equals 0.5546. I'm going to round that up to 0.5547 because it's 469. 0.5547, or 55.47%. If I dump that into my calculator for my angle theta, same as we've been doing, is cos -1 or -1 cos, I can never remember, of 0.5547. And that equals, second cosine, second answer, that equals 56.31 degrees. So I'm going to have a lag or a lead of 56.31 degrees. And I'm going to erase a little bit of this to draw that sine wave. So here's my sine wave. Now, am I ice or am I Eli? Well, let's go to my powers. At the capacitive reactance, the power reacted at the capacitor, I had more bars than I had at the inductor. I had fewer bars. So this is a capacitive circuit. So I'm dealing in ice. So my current is going to lead my voltage. So I'm going to draw my first sine wave, and then my second sine wave is going to be 56 degrees different. Now 56 is a little bit more than halfway to 90. So I'm going to draw that second sine wave here. I'm a little bit more than halfway to 90. I'm going to label that 56.31 degrees. And then I'm going to label my two sine waves. And I'm going to say, well, if I is before E, then I got to label I before E. This is my current sine wave, which leads my voltage sine wave, or my voltage sine wave lags my current sine wave. That 56.31 again is this angle right here on any of the resultant triangles after we solve these two things, because I have both in there. That's the angle I want. We'll go over this again. I'll make another video next week, hopefully without as many silly errors. But you can see what we're up to here. And this will not be on this week's quiz. This will be on next week's quiz. So as you're watching this video, hopefully you watched it in the week I've asked you to, because there'll be another one next week. I want you to keep up on your videos. This business will be in next week's video. That's all. Hope that makes sense. Email me, text me if you have questions. I am happy to answer those questions. Sometimes I get your texts when I'm not right there in front, but we'll see. Somebody just left me a note. Bye.